But yeah, thanks for inviting me here. And my name is Emtiyaz Khan, but just feel free to call me Emti. And I'll talk about the Bayesian learning rule and some of the recent work that we have done on building adaptive AI systems. The slides can be found on my webpage. And you can also see a poster that I've recently made where I've summarized some of the work that we have done in the last 2 years. And thanks to these individuals who have helped prepare many slides in the talk. At least one face there is very familiar to you. All right, so let me just start with the big picture. The goal that many of the machine learning researchers are interested in is the design of AI systems that can learn as quickly as humans and animals. It's something that I've been focusing on for many years now. The feature of humans and animals where they can quickly adapt to new situations that arise in the future while robustly preserving and using the past knowledge. And if you've seen my talks before, you've seen this sort of motivation that I show of my daughter when she's younger. She's trying to figure out what she likes and dislikes in the world, what is relevant information, what is irrelevant. And by some random exploration through the world, she can sort of figure out that the sound that comes from this instrument is very relevant to her. And once she figured this thing out, she can now go on to explore novel situations where she can get the same kind of experience from the world by any means necessary. So this sort of quick adaptation is a unique feature of human learning and animal learning, and something that AI currently is not very good at. So this kind of learning requires a delicate balance between the past and the new information. So sometimes if you're too keen on the new information, so you're too quick to adapt, you may actually fail. So this is an example of Tate Tweets, the Microsoft AI chatbot that was put online in 2016 one fine morning, and then throughout the day it learned from some Twitter trolls and overfit to that data that it saw that day. So it had to be taken down after a day because it was too quick to adapt. But similar things can happen when the system can fail, when it's too slow to adapt. So robotics, this is a very common scenario where if you change slightly the environment and the robot cannot quickly adjust to the new changes because it's holding on to the old information that it has learned in the past. So the point is that, if you want to do this kind of adaptive and robust learning, then you need to do this balance between old and the new information. And my goal here is to kind of argue that whenever you want to do this kind of learning, then there should be a Bayesian side to it. And it's kind of inherent, it's always there, is something that I want to argue. So start with what are good algorithms and what are their properties? And it turns out the argument that I'll try to make is that there is an inherently Bayesian side to these algorithms that must balance the old and the new information. And something like Bayes' rule, something like solving a Bayesian problem is what a good algorithm must be doing. So this is the hypothesis that is being put forward. So I'll show you the first kind of start with this Bayesian learning rule, which tries to make this concrete by showing that many good algorithms that have been found to work well in practice, they all can be written as a Bayesian learning algorithm, which I call Bayesian learning rule. This is a specific type of learning rule, but it's quite general in the sense that you can derive all of these good algorithms by making certain trade-offs, Bayesian trade-offs in this Bayesian learning rule. So that'll be the first thing. Then I'll go into robustness, so how we can use this learning rule to show that there is some robustness property that good algorithms should have. It should preserve the old information. And I'll introduce a concept called memorable experiences that is being derived from these Bayesian ideas. And then we'll use that in adaptation. So we'll show that by using this kind of concept of memorable experiences, we can do a good trade-off between robustness and adaptation. So I'll introduce something that we call now knowledge adaptation priors. And so that'll be the talk. The whole point here is to say that to do the balance between the old and new information, you need to be Bayesian. And here's a new perspective of Bayesian that helps us to kind of design practical algorithms that can make it possible to do a good trade-off of adaptation and robustness. So the papers that I'll be talking about today mostly is the first reference, and then there are some others that are kind of for the other parts. Most of them are out except this one paper that just takes really long to do. So I hope that you will read those papers maybe after the talk and find this to be a useful work for your own research. All right, so let me now start with the first part. So what are good algorithms and what are their properties? That's the question that we start with. And the question here is very similar to Origin of Species, which was about like, what are properties of natural algorithms? So living beings, they all originate from some common origin, and they're all kind of similar in some sense, yet different because of their condition, because of natural selection that has happened. Here we are arguing about not natural algorithms, but rather artificial algorithms that we use in machine learning, for example, and in other related fields. What are the origins of these kind of good algorithms that we use? And one thing that is clear that we may agree that good algorithms must revise its possibility by using some useful future information. So no matter what scenario you're putting them in, if they are learning from data, then you must be somehow figuring out if the new information is useful for your old knowledge that you have, and then trying to squeeze that maybe through gradients or some other kind of mechanism to squeeze that information in your model. So then what we are arguing that if all good algorithms have these properties, then there should be some kind of common origin in what these good algorithms optimize. So what kind of objective function they optimize and how they optimize it. So with this idea, we put forward this hypothesis that the origin is perhaps Bayesian. So what these algorithms are optimizing, they're not like what we usually see in machine learning, like minimizing a loss function and finding one point estimate, but rather it is something Bayesian where we are trying to find a distribution. So we're trying to minimize the loss, but we want to now minimize over the samples from a distribution. So all of these samples should also give us low error, but then we regularize the entropy, meaning that the samples should be away from each other. So there should be some diversity in the samples. They should not all collapse to a delta distribution, right? So if some of you, who know about optimization formulation of Bayes' rule, you may know that this is like variational inference. So there's a posterior approximation that you could use. And we're going to use exponential family throughout the talk, but it's not really variational inference because the loss may not correspond to a proper probabilistic model, but it could be just kind of an arbitrary loss. So it's a slightly more general way of writing this. Some people call it generalized posterior. In the, like, for example, pack-based community and in online learning, also these kind of ideas are used. So it's just slightly more general. but it is a Bayesian formulation. Okay, so the first argument of the paper is that we optimize something like in the right side. And then the second point is that we should be optimizing using a specific learning rule that that makes use of some kind of information geometry of the problem. So to be specific, suppose we use an exponential family, then its natural parameter is updated using these gradients, and the gradients are taken with respect to the expectation parameter. So if you actually know exponential family, then you may remember that natural parameter and expectation parameters are they sit in two dual spaces. So there's some kind of like duality, some kind of information geometry that's being involved in updating the natural parameter using the gradient with respect to the expectation parameter. The thing that I want you to see for today's talk is that you can see this sort of convex combination of your old parameter as, old parameters and the new gradient as something that you have like old belief incorporated in the old natural parameter, while the new information is coming through natural gradients. So these gradients with respect to mu, they're special type of gradients that are sort of using Fisher information matrix inside. So that's how the information geometry comes in and the duality comes in. And using the natural gradient, you're updating the information. So you can see the natural gradients as innovation. They're new information, and you're taking a convex combination of the old information and the new information. And so this is how we're saying that there is a trade-off between the new and the old information. I'm happy to take questions at any time, so please interrupt me. By the way, if you're not familiar with exponential family, just think of this as Gaussian distribution, and that'll be enough for you to think through these things. So we'll look at some examples of what lambda and mu look like just in a minute. Okay, so this was kind of, it is written now in the Bayesian learning rule paper, but originally it was proposed, the algorithm was proposed in 2017. It's taken us 5 years to kind of confirm that what we have been suspecting for all this time is indeed true, that what you can do is you could take this algorithm and you can make two choices. One is of posterior approximation. So you can change this Q. You could choose it to be a Gaussian or a mixture of Gaussian, a Bernoulli, or any kind of exponential family, or a mixture of exponential family. And then you can do certain approximation in the innovation, the new information that you get through natural gradient. You can choose, you may not use the full natural gradient, you may do certain approximation to it. And by these two choices, you can derive many types of learning algorithms. So for example, gradient descent, you choose it to be Gaussian, fix the covariance, and use some approximation on natural gradient that will give you gradient descent. Okay. There are other things here that I will get to in a minute, but let's just try to look at this first. This is the simplest example, and it's almost trivial when you look at it, but this example gives you an idea of how this rule is applied. Okay. So gradient descent is this update, and now we're gonna choose Gaussian in the Bayesian learning rule. You're gonna fix the covariance. You can fix it to anything you want. We're gonna fix it to 1. It doesn't matter really, but for simplicity, we'll fix it to 1. And then you do the math, you write down the exponential family, and you look into like, what is natural parameter? Well, it turns out the mean is the natural parameter. What is the expectation parameter? Because you only have like theta is the free parameter because Gaussian is quadratic, but if you fix the covariance, you only have one free degree of freedom. So the expectation parameter is also just the mean. So they're both the same, and the entropy is constant. For a Gaussian, when you fix the covariance, the entropy doesn't change. So then I've written a Bayesian learning rule in slightly different form where I've written the entropy explicitly. Sorry about that, but now you just plug this thing in. So you plug mu, you plug the, you get M, lambda, you get m, and entropy is constant, so just kind of disappears from here. So you get something that looks like gradient descent. Okay. It's almost the same. The only difference now that you have that the gradient is kind of taken with respect to the expectation of the distribution. Here, there's no expectation. So this is kind of a non-Bayesian version, and this is a Bayesian version. So when you want to go to the non-Bayesian version, then you have to ignore the distribution and only look at like one point. So we'll choose it to be the mean. And that's what this approximation is called. So this is the natural gradient approximation. And once you do this, then it's kind of equal. Okay. So whenever I present this, people don't like this delta method. They say, well, you're cheating, you're removing this expectation. So of course you get something that looks like this. But I want to talk a little bit more about why this expectation, the Bayesian part is actually important. And gradient descent doesn't have that expectation, but it turns out stochastic gradient descent has some kind of noise source. So it looks more like what the Bayesian learning rule suggests than what the gradient descent would do. Okay, so that's the next part that I want to get into. So essentially what I'm going to do that now I have written derive gradient descent using a approximation to the Bayesian learning rule. I'm going to try to remove this non-Bayesian approximation. So the delta method, where I computed the gradient only at the mean, I want to now put the expectation back in. So I'm going to remove the delta method. I'll put the base back in, and what we'll see is that we'll get methods that will sort of do more Bayesian things, and we'll see that they're expected to be better. They have better properties, which is what we would expect with the Bayesian method. So I want to spend like next few minutes on that. But if anybody has any question, I'm happy to answer. Okay, many of you might have already seen all of this stuff. So let's get to some new parts now. So before going into why putting expectation back in there, why is it better? Let's try to first look at a very simple intuitive example. So suppose I choose my Gaussian, my distribution to be a Gaussian with the mean mu and covariance, let's say this in one-dimensional case, it's a sigma square. Then I could look at what happens when I put the expectation back in, right? So this is a simple example. The losses is this kind of non-convex problem. You have multiple local minima here. But what I could do is I could do this expectation, and now I can plot the loss with respect to the mean and the standard deviation. So that's what I've written here. This is the mean, that is the standard deviation. And what happens is that as I increase the standard deviation, I get more smoothing of the loss function. So all of these weird local minima that you have here, they're probably not that stable places. They're not that dominant. And as I increase the covariance, the variance, these unstable points kind of disappear. So there's some kind of smoothing that is happening, right? So another way to put it is that instead of optimizing the original loss, we are trying to, using these Bayesian principles, we are trying to optimize for a different one. In this case, it's a smooth loss. This idea is kind of catching up now in deep learning. It's under this point of implicit regularization, where people are showing that SGD actually doesn't really minimize the original loss, but it minimizes slightly something different. Okay, so but this idea is actually quite old, and it has been used quite a bit in optimization, like smooth optimization, perturbed optimization, continuation method. There's a whole lot of techniques. Simulated annealing is another one where this kind of like annealing and temperature ideas are used to sample. So this idea is not really new. It's a very old idea. But to put it in a new context, we're going to now try to understand what happens when you do this kind of smoothness, right? So when you use gradient descent, there's no expectation there. So there's no smoothing of the loss function. And essentially, the stationarity condition is that the gradient of the loss at one point is 0. Okay. Now, if you look at the Bayesian learning rule, the version that I used to derive gradient descent, there is an expectation here, and the gradient is taken with respect to the mean. And if you think about the fixed point of this rule, then it's essentially kind of taking this gradient of the expectation and setting it to 0, right? So this looks sort of different from that, but you can do some tricks. So there's something called Bonnet's theorem. It's in the paper in equation 25. Essentially, what you could do is you could push this gradient with respect to the mean inside the expectation. Okay, so that's what I've done here. And now it looks a little bit similar to this, as you can see. So the gradient is taken inside, and now you're sampling from a distribution and you're plugging. Now you want the gradient at many samples from this distribution to kind of go to 0. Okay. Sorry, I'm feeling a little bit dizzy right now while talking too much. So take a little bit of break. Okay, so the point here is that the Bayesian solution that injects this noise, it has some kind of regularization effect. So instead of looking at this kind of point estimate, now we're looking at a Bayesian solution where the noise is being injected. And what I'm going to show you is that in SGD, in stochastic gradient descent, the noise plays a very similar role to the noise that is being injected from the Gaussian in this equation. Okay. So the summary is that the noise kind of makes you go towards a flatter direction, like what happens in SGD. Okay, so we're going to look into a very simple example. So this is a one-dimensional example, and I'm sorry, I'm not feeling very well for some reason, so to slow down a little bit. Okay, so this is a one-dimensional example, and it's kind of an unsymmetric loss. So the mode is here, the minimum is here. And if you go that side, then the loss is very, very large, right? So you have a wall. So you're hitting a wall on this side. But this direction is flatter, okay? So what we're going to show in this example is that SGD is going to go, the solution will be pushed towards this side. And then the Bayesian solution also have a similar property. Okay. So let's start with SGD. This is the same example as what I've shown in the previous slide. So this is the minima, and you can't really see that the loss function goes slightly up here because of the scale. But that side is the flatter direction, and this side is the wall. So if you use SGD with step size very small in this case, then the iterates are kind of close to the map estimate, and it really converges to the minimum. But as you increase the step size, like learning rate, then the steps sort of tend to go away from the wall. So let's increase it further. And you see that the Gaussian is sort of going away. And you can imagine why this happens. It's because the loss on this side is really, really high. So with high learning rate, you're really kind of hitting the wall many times, and that pushes you in the opposite direction because the noisy gradients are really kind of large to that side. If you increase the size, step size a little bit more, you go really on the other side. Okay, so here's the summary, just for you to see it visually a little bit more. I hope you can see in this very, very simple example, it's not even deep learning. And I think this is logistic regression, one-dimensional. And you see that the iterates kind of really move to the flatter direction, right? So the iterates are really going towards that side if the learning rate does not decay to 0. Now, what I say is that if you do the Bayesian update, you have the same effect. So if you, let's say, fix the covariance to 1, like what I did in the deriving SGD, then this Gaussian tend to be away from the wall because like I don't have flexibility to reduce the variance. So it's trying to kind of avoid this wall. And it's kind of the zero avoiding property that you read in Bishop, and many times people say it's bad. I think Rich has done a lot of work on this, saying the mean field shrink the variance, right? But here I'm kind of showing that somehow it's actually, it's nice. And maybe it is nice in some case, we don't know yet, but it has some kind of regularization effect that it's going towards the flatter direction, right? But why does this happen? It's actually quite simple. It's just because of this equation. So I will encourage you to look into the figure 1 of the paper. So essentially what happens is that you want to find the distribution, but because you want the samples from the distribution to cancel each other out, all right, because the expectation of the gradient should be 0, you tend to assign lower probability to large gradients. So the gradient on this side is really large. Gradient on this side is small, and you need to cancel those two. So you put a smaller weight. The red line is small here compared to the probability mass here. Right? So expectation has to be 0. So the distribution shifts to the other side. So you're kind of going towards the flatter direction. So it's more robust. I shouldn't call it implicit regularization. Actually, I meant to change this. It's explicit regularization. But you notice that regularization is not from the prior. Regularization is not from it's not explicit in that sense. The regularization is in the posterior approximation. So you're saying that if you choose the posterior to be a Gaussian and you fix the covariance, then it has this its property that it goes to a slightly flatter direction. In the next part, we see that if you actually let the covariance be adaptable as well, you go to flatter minima. So it's not like the method changes, but it's actually a nice property of Bayesian principles that it will lead to a more stable places. You can get this effect by changing the variance in the variational approximation. So in SGD, sorry, this graphic is not very good. It's not complete yet, but in SGD, you can increase the step size, right? And you go farther and farther. In the blue is like Bayesian approximation. So if you increase the variance, you can get a very same effect. And it's always kind of convergent, right? So you can get farther and farther, and you can get arbitrarily far by changing the noise in the distribution that you inject through the distribution. Okay, so I hope that this is a convincing story, but I put this meme there, first meme for me, to say I'm really asking. Well, I shouldn't be asking you guys because you're probably more Bayesian than me, but I'm asking the community to be more Bayesian because we want to put the expectation back in. We shouldn't be looking at point estimates. We should be looking at samples from the distribution in some way. So this has been our effort in past few years where we are kind of saying, let's try to put this expectation back in. So the way we do it in the Bayesian learning rule is that we know that by putting this delta method where we remove the expectation, we can get all of these optimization methods. So like RMS prop and Adam, you have this delta method. So now we're going to remove the delta method, and that will give rise to these other methods where we can estimate the variance, and we'll have the expectation back in. So we're always injecting this Bayesian noise. And we hope that these methods will somehow give something better. They will be slightly more improved. So I don't have time to go into that, but essentially these BLR variants that we have been working on for past few years, and some with collaboration from people in the room. So we have written these 3 papers, for example, and they've been sort of trying to improve things by making less and less approximation, making these algorithms more and more similar to RMS prop and Adam. And this is what led to the winning solution this year in 2021. So Thomas and other people in the group, they actually did this method, and you can watch his talk if you're interested in this. This 3rd paper is what I think is the new thing that has happened in last 2 years. Okay, so I will skip this part. Essentially, the next part is kind of trying to explain how these algorithms are obtained. And I've given a talk before about this maybe in 2019. I talked about this when I visited you. But essentially, the message is kind of like, if you increase the complexity of the approximation, like for example, you add the covariance, you go from first order method to a second order method. So it has a very nice property that you can relax more assumptions and you get better and better methods. So, which is what you would expect from a principle that if you approximations are less, then you get better, and the goodness of the algorithm sort of increases. And we have that property. So if you go from Gaussian with covariance to mixture of Gaussian, you get kind of mixture and ensemble method. And really the Bayes is really there because Bayes is trying to repel these samples from the distribution or these different components of the mixture of Gaussian away from each other. So Bayes really helps there, and it shows up in the rule. Okay. So yeah, I'll skip this Newton's method to obtain that. It's always the same mechanism. So you write down the distribution, you write down the lambda and mu, the 2 parameterization, you plug them in, you do lots of like simplifications, you invoke delta method, you get Newton's method. But essentially kind of it's trying to do something like, robustness. So now you can choose the covariance, so you can go from sharper minima to flatter minima. It still kind of works. Okay, it works on ImageNet. I'll leave it at that. And that's the winning solution, an improved version of Vaughan algorithm, which is easier to implement than Vaughan. It's even closer to RMS prop. It's in this 3rd paper by Wu Lin. So I will encourage you to check that one out. Okay. So if you want more details, there's this new tutorial. This hopefully this part, for some of you, you have seen this, but there's some new stuff here, at least in terms of motivation. So I'll spend maybe like next 10 minutes or so to talk about the new things about adaptive AI and why I think that this work is important. If you have any questions, I'm happy to answer. Also gives me some time to breathe.
Emti, a quick question. So you said that the loss doesn't have to include a prior, and that's kind of key to some people's perspective on what Bayesian methods are. And the prior didn't really feature in anything that you said. It wasn't sort of explicitly required for this property that was going to seek out flatter minima, for instance. How do you think about that, and how do you sort of connect it? Does Bayesian here mean essentially distribution over parameters is being used as opposed to a point estimate? Is that the sense of Bayesian which you mean, and therefore prior is not not central in that sense?
Yeah, so I mean, it's Bayesian. The prior has to be there. So, of course, yeah. So, if you don't want to use the prior, you may not. So the principle of entropy regularization, like maximum entropy principle, as put forward by James in 57, doesn't really say much about the prior. But of course, later on in his work, he writes about that, and it is clear that the prior is extremely important. So there has to be a base probability from which that defines, how you measure the distance to the new distribution. So the prior always has to be there. But what I'm saying is that in terms of deep learning, the prior doesn't have to be explicitly doing something very clever, right? I'm saying in deep learning, when people talk about implicit regularization, the explicit regularizer, maybe it's added through weight decay, but that's doing very little. Okay, maybe it's only providing some kind of slight regularization to make some ill conditioning go away. But the regularization that's happening through initialization, through SGD, like mini batch noise, that's actually much more powerful. And we don't know how to write a prior distribution or inductive bias. I think people are talking a lot on Twitter about this. We don't know how to express this. And my point here is that you can look at the approximation, you can look at a posterior approximation, you can look at what sort of choices people are making when they're running these algorithms. They show up in the fixed point. And from there, you can work backward to design a good prior for the next task. So that's where the continual learning work comes in. So when what we call K-prior, knowledge prior, and knowledge adaptation prior, the work that we did with Siddharth, and also FROMP, the work that we did, it's sort of trying to bring out this prior information by looking into the posterior approximation. And it's not saying that everything is explicitly written out, in the classical sense of Bayesian priors, but it's somewhere there in the solution that you have found. So you can start from there and do something afterwards. Does it make sense? Sorry, long answer.
Okay, thanks. I've got a quick question as well. Your description of like why this finds about a minimum with this kind of cancelling out of the sharper side on a symmetric distribution, with it kind of pushes it toward the planar minima, so that this derivative is zero. Does that mean that it would be fine with sharp symmetric minima? Because that feels more about like the asymmetry of the minima rather than the sharpness.
Yes, I agree. Yes. So, I mean, again, in the simple cases, like if you have a symmetric distribution, then regularization will be at asymmetric local minimum, right? But you can have slightly different distribution that captures the neighborhood, and through distribution you can actually design these kind of implicit regularization that will be there in the solution. Does that make sense? Yeah. So like changing the covariance, that's another way to do things, but you can have some skew. So you say some directions, maybe let's go to the biggest eigenvalue in that neighborhood. So it'll go in that direction. So actually with memorable experiences that I'm going to talk about soon, something like that is happening. You don't kind of directly specify that because it's hard to know what part of the spectrum is useful, like which flat direction should you go towards. You can think about it better in the data space, like which data example should I align my predictions to, And it's a very beautiful thing that's coming out of this work. That is the next 10 minutes that hopefully I can spend. Is that okay? All right. So I'm sorry, I'm a little bit not feeling very well today, so I go a little bit slower, and I apologize for. So let's kind of go, like, how do we go towards preserving information and adding new information, right? So let's say that all algorithms are Bayesian, and let's say all good algorithms are Bayesian. Let's say if you accept that hypothesis, then somehow when we are adding this new information through these natural gradients, good algorithms should be able to tell apart what is relevant and what is irrelevant. So if the new information comes in, through natural gradient, then suppose if you converge and you bombard the solution with new data, the solution should be robust somehow to if the information that's in the new data is not new. Right? So there's a sense of stability in the solution. And this is kind of the way to understand this new type of regularization that we are thinking, that how far away the solution should go, it's harder to specify through this Gaussian approximation. So now we're going to think about an alternate way to, preserve and adapt the old information that is present in the model. So I've been thinking about this for some time, and so it's very beautiful. It's taken me 3 years almost to get to this point. What I kind of see is that the central concept here is of how sensitive things are to perturbation. So perturbation in the model through maybe data or parts of the model through some kind of intervention. So we stop certain parts, maybe certain data example, we freeze them. We try to see how much the model's performance is sensitive to it. And that should actually help us understand what knowledge is worth keeping, preserving, what knowledge should be changed. Right? So this is the idea. It turns out that this is, is related to, it's encapsulated in this term called duality. And it's a very loaded term, of course. So if you're not able to see the point of duality, think of perturbation and sensitivity. How sensitive things are globally when I perturb certain parts of the problem. So it turns out that this sensitivity can almost be read off. You can get it from the BLR solution. It's there. So because it's kind of written in this way that there's new information in natural gradients, they also tell you which parts are more sensitive. And this is extremely simple to me right now, and I hope in the future it'll be to other people, but very profound insight that I couldn't believe myself in 3 years ago when I was thinking about this. So if you suppose you have a problem where the problem consists of many examples. So you have many examples and you have a prior distribution. So there's like n+1 terms in your loss function, regularizer, and n data points. If you write down the Bayesian learning rule, you get something like this, very simple, sum over all the natural gradients here. Right. If you look at the fixed point of this that we get, you see that the solution, the global natural parameter, call this global natural parameter for the full distribution, it consists of many smaller components that are contributed from each part of the loss function. Okay, so these are natural gradients computed on individual losses, and I'm going to call them local natural parameter, denoted this by tilde. So tilde means local. So you can see almost that the lambda tilde, if it's big, then it contributes more to the global solution. So the data examples that have larger value of this natural gradient should somehow be more important to specify the global solution. And this kind of makes sense because they're all additive. And these are, I used to call this conjugate computation, but people don't understand that word. So I hope that you see that you're summing up lots of information. These are innovations in each data example. They're summed to get the global solution, and some of them are more contributing more than the others. Now, the fascinating thing that I've discovered, and I've worked on this problem for many years because the first paper that I wrote was in 2012, 2013. It turns out that these quantities are also dual variable. So these natural gradients, they're actually Lagrange multipliers to some moment constraints. So actually, it has very similar property to what people have found in EP. So these kind of site parameters, they tell you when you leave out one factor, how much the things change. So they have some kind of, perturbation to if you leave out this example, what would happen to the global distribution. The same thing happens also in this kind of variational formulation, that these things are measuring the sensitivity to the change in the marginal of the distribution. So this originally I wrote in 2013 in a dual variational inference paper, and I wrote another one in 2014. And now I understand the connection to natural gradients. So we wrote a recent paper where we write this for GPs. So you can read that one. And the idea is basically that because they're Lagrange multiplier, they tell us what happens when you remove the state example, what happens to the total. So it's not just kind of an intuition. It's actually very, very profound fact about the Bayesian objective, that the natural gradients are also the Lagrange multiplier, and they already tell you about the sensitivity of the problem. So you don't have to compute it again. When you get the solution, you already have it. Okay. So this is what we're going to use to tell apart the relevant versus irrelevant data. Now, I don't have time to go into this. I'll skip this part, but I'll show you. So we've been kind of working on this memorable experiences idea, where it turns out that you will look into these lambda tilde i's, and you can characterize examples of different kinds. So they have different kind of sensitivity. So easy examples are classified all correctly. But then the ones that are outliers, so this 5 is mislabeled, but you can look into lambda tilde, and in the Gaussian case, there's kind of usually 2 entries, and using those 2 entries, you can characterize 4 types of example. I'm showing you 3 here. So outliers are another kind of example that have different lambda tilde, and then uncertain examples are these weird looking example that whose lambda tilde differs from the others, okay? And there is a 4th category, which is both outlier and uncertain. You can't tell between the 2. Okay, I'm skipping the details here, but I hope that you've got the main point that the posterior approximation, when you do it, you compute natural gradients through posterior approximations. So if you use a Gaussian, you have 2 sufficient statistics. So 2 criteria emerge that gives you 4 types of examples. These criteria naturally emerge. I didn't make it up. I didn't have to choose which type of example these are. So I didn't have to kind of go and say, I'm going to use a hinge loss that will give me support vectors. I'm going to design some kind of perturbation function that will give me some kind of influence. Or I'm not going to do something like an optimization of the elbow to get inducing inputs. All of these concepts are now kind of built in through memorable experiences. So we're writing these things down in this, and Siddharth Swarup is also involved in this work, but it's taken us very, very long time. So it's unfortunately still not out. But the point is that it's kind of things naturally emerge, and these are easy to compute. So okay, 50 minutes are used. So the idea here is that this kind of sensitivity, this is very unique and it's very general. And it generalizes many kind of duality concepts that people have used in optimization, also in non-parametric, like Gaussian process, like Grace Valva's work from the 70s, work on kernel methods, support vector machine, all of this other robust statistic stuff, all of that kind of comes together now through this very simple equation that comes from the Bayesian learning rule. So the natural gradients are key quantities there. So we're now really building this up, and we are very fortunate to get a lot of funding lately for the next 5 years. So we have around 3 million USD through 2 grants from Japanese governments, and there are a couple of people involved from France, and also some people like Rich is also part of this group. So if you're interested in working on this, and if any of this appeals to you, please feel free to reach out to me or Rich or Siddharth or some other people who work with us. Okay, so I'll just kind of quickly end. I won't go into the detail of this, but you almost know the important point about this Lagrange multiplier and the dual variables. But essentially, this is what we have done in the past, and that work predates the Bayes duality term. So the duality is not used. The term dual is not used in those papers, but essentially, the idea is that you look into the dual variable. So suppose you're given this kind of classification problem, you fit a model, you find the dual variable lambda tildes in the solution of that. you pick through some, thinking what kind of memorable experience might be important for you. Maybe you want to preserve the performance, so you pick the ones that are close to the boundaries. So in this one, we pick the uncertain one, and then you freeze them. And then when you train the next set of data, you just want to make sure that you don't lose the performance here. So this is a different way of pushing the solution into a type of like flatter direction, because you're making sure that the perturbations align to some of these examples that are being chosen and frozen. If they're chosen appropriately, you don't know what's going to happen in the future, but if you chose it in the right way, if you made the right decision, then the payoffs are really huge. And that's basically what happens. Okay, technical details, when you look at it, and you may get lost in it, and you may think that we are just kind of not doing anything new and doing some weird mathematical tricks where we're converting things to Gaussian process. But these are all kind of, mathematical details. Eventually, you would write this kind of Bayesian problem. You will somehow try to trade off the new information to old information. Usually people use the weight posterior. So this is variational continual learning, essentially. But now we're saying that let's not just use the weight regularizer. Let's look into the dual variables. Let's go into the dual space. And turns out the dual space of this kind of model is actually a GP. So then everything, you look into the dual variable, and there's two types of dual variable because it's a Gaussian, and they're two kinds of things. So when you write down this dual regularizer, essentially the parameters that connects to the mean tries to make sure that the predictions are matched. Yes, the mean is kind of more about the prediction. And the points about the uncertainty, like uncertain examples, they're more kind of about weighing which example is more important than the other. So the two types of dual variable do two types of things. And that just conveniently comes out of the math. And you don't have to like tweak it. So we've been working on this for some time. So this dual parameterization is actually found using Bayesian learning rule. If you read the paper, pay attention to that. And this is a central point that many people do linearize neural network, and they don't cite our work, and then they say, well, this is very complicated. But what they're not realizing is that I don't have to pick which point to linearize that. Everything is coming through natural gradient. It's telling me what linear model, what Gaussian process to use, because I go into the dual and I look at the dual, and just kind of dual tells me the importance of how I should be doing transfer. And essentially what happens when you do it right, so now we're doing this thing called K-prior, where we show that this kind of function space, it's a combination of function space and weight space. It can faithfully reconstruct the gradient of the past. So why it actually works is because it's very principled. It does a very, the right thing that you would expect, that it somehow represent the past such that the gradients are reconstructed. And in the paper, we show that all sorts of adaptation mechanisms, those used in SVM, in knowledge distillation, in online GP, like from Sato and Opert's work from 2001, all of these things are essentially a form of K-prior. So they're always kind of reconstructing some kind of gradient of the loss, maybe gradient of the elbow, something. So there's a very strong indication that good adaptive algorithm must have a Bayesian prior to them. And this is very neat. This is just a simple illustration. If you add one, example, then the gradient's almost kind of same here. It's the gradient in the weight space. If you increase the number of examples, then the gradient kind of keeps getting closer and closer. And I'm sorry that I went too quickly over these things, but I hope you can look into these papers, these 5 papers that I've listed here. Essentially, it's a new perspective of Bayes. And really, like everything, it's not about like using Bayesian learning rule or memorable experiences like K-priors. It's more about everything goes through the approximation of the posterior. You choose the posterior approximation that naturally does the right kind of, choosing the information. And so that's the key point here. You can do the posterior approximation, you can look into the primal view, or you could look into the dual view of it, but it kind of does the job that you would expect it to do. So now we're really working on, 3 ideas like knowledge representation, knowledge transfer, and knowledge collection to design AI that learns like human. There's a lot to unpack here, and I'm sorry if I went overboard with the message, and I apologize. I'm not feeling 100% today. I'm a little bit dizzy, so I had to speak slower. But this is the people in the group, and I'm very thankful to have collaboration with people. So Rich and Siddharth and Eric. Hope I didn't forget anybody else, but yeah, we have lots of potential for collaboration. If you're interested, I'm happy to talk about it. Thank you. Thank you.
If anyone has questions, now is a good time to ask them. If you're on Zoom, you can just unmute yourself and ask a question. Javier, you can go ahead.
Yeah, I have a question. Thanks. By the way, thanks for the talk, Emti. It was very enjoyable. So you mentioned briefly the linearized models from some of your previous work, and I guess I wanted your opinion on whether you think that linearizing a neural network is just a vehicle to allow us to perform approximate inference in that model, or if we're switching the model to a different model, to an affine model perhaps, and doing inference there, and what are the implications?
Yeah,
of that?
That's a great question. Yes. No, I don't think that linearized model is good enough, because if you look into the math, the linear model will always come whenever you use a Gaussian approximation. So the paper, so this third reference here, the one that I have had the most difficulty to explaining it to people, if you look inside, you will see that it's showing that through Bayesian learning rule, that Laplace approximation and variational inference, its solutions, or algorithm, the iterates, they all give rise to some kind of linearized model. So essentially the point is that whenever you use a Gaussian, it corresponds to using a quadratic approximation of the losses, right? So that's why you get a linearized model, because it's a losses becomes a Gaussian one. So I think it's a mean to do approximate inference rather than it being a sufficient model in its own. So I know that many people think that if you could do NTK and then everything will be great, but I don't feel that way. I think better approximation will give you better surrogates. So like if you do mixture of Gaussian, that will give you, an ensemble style. So like it's a multi kind of local, many local minima. So it's necessarily better. We just need to find the right posterior approximation that will be enough to somehow come close to what deep learning performance is happening, So maybe you need many local minima, maybe Gaussian with this kind of mixture is enough. Maybe the Gaussian process view with some kind of dual representation would be better. I don't know right now, but that's how I would like to see it. That's just kind of my way of thinking. So does it make sense?
Yeah, it does. Thank you.
Okay, thank you. Yes. Hello.
I wanted to ask something very unsophisticated, I guess, which is that sort of you've presented a fairly large number of works, and the literature sort of on this topic is getting sort of bigger and bigger and bigger. And for somebody who is not familiar with either kind of the learning rule point of view that much, or with continual learning, what's a good way kind of to dive into this literature? Like where, like if you have like, you know, some technical knowledge, but sort of from a quite different point of view than the one presented, like where would you start?
Oh, that's a hard question. You know, this is a hard question because I tend to, so you use the right word, large number of papers, right? My opinion, and I'm a little bit cynical because I'm also, you know, been doing this for a while. So you may not want to listen to me, but I'll give my cynical view anyway, because since you asked. So my opinion is that people try to see, so there's a large number of papers written, right, on continual learning. Of course, people somehow tend to believe that if you tweak losses architecture, somehow you can solve this problem that's kind of, you know, is a fundamentally very difficult problem. So I would say read less, because if you actually look into, I mean, you know, try to go away from neural network and try to write down the simpler problems where you want to do this kind of continual learning. And, you know, you would see the difficulty that there's no free lunch, you know. When you don't know what's coming in the future, things will completely kind of be, if you make a wrong assumption, you will pay a huge price. So somehow when we pretend in these papers that we do these tricks and that can solve the problem, I think we're missing the point. So we really need fresh perspective on these problems. And again, this is a cynical view. So I would say we need more foundational work, more fundamental work, and less kind of looking into all sorts of tricks that people do to somehow gain 1%. I mean, don't read my paper even if it causes the noise in your brain, you know. So read like maybe EWC paper was a nice paper, I think, and some old work on SVM. In K. Pryor's paper, we have a lot of those references. So you could look into adaptation, for example. There is quite a lot of work on that, on how do you adapt a model that has been trained and now something changes, what you must do. And this change could be like any kind, you know, it could be you change the data, or you changes the, you know, maybe like Lasso kind of model where you decide to use a different higher regularization strength. How do you quickly adapt it? This is already a problem, right? And you will see how fundamental things will come out of there. So I think that's much nicer to do. Sorry if that's not the answer that you were looking for.
Yeah, I was actually thinking specifically with your work within this space rather than like the space at large, which is more the question that you answered. Like, but actually, I appreciate the answer to that question too, because I think, you know, to understand probably your line of work, one probably also needs to understand the context. But among your work specifically, I would follow up to ask, like, what would be like a good starting point?
If you want to read one thing from my work, this is Bayesian learning rule is the thing. It took me 2 years to write it. And I think the next thing that you want to read, if you don't want to read any other thing, then read this memorable experiences paper. It should be there at some point this year. So we have taken 2 years almost writing the paper and 2.5 since thinking. So I hope that this paper will set things right in terms of how we should be thinking about core sets and like representation of the trained models. Yeah. So we're trying to write something foundational. I hope we succeed.
Okay, so then the papers you would recommend are the Bayesian learning rule now and memorable experiences of machine learning models once it's out.
Yes, 1 and 2.
Thank you very much.
Great.
We have some more questions from the room.
Cool. Yeah. Hi, Emti. Thanks for the talk. So I wanted to ask a more practical question, maybe. So in the Bayesian learning rule, you have this whole like nice table that you showed us, right? How you can different variants of that rule that you can derive. So now, yeah, exactly. So now if I have a a learning problem? Like, is there any guidance that the Bayesian learning rule provides to tell me which of these algorithms I should choose or what I should try first or something like that?
Yeah, that's a great question. Yeah, so the way that I usually approached, like the way we found these things here in this table, for example, right? So you see mixture of Gaussian, you see Bernoulli distribution for like binary neural network. I think, right now in the field of optimization, deep learning and approximate inference, like hierarchical Bayesian models, what we do, most of them are tackled with mixture of exponential family. So I think that should be the first kind of thing that you try. So I usually try to think about what kind of information is important in my loss, right? So the problem that I write down. Yeah, unfortunately, it requires a little bit of more understanding of what natural gradients look like. So I would encourage you to read the first sections of the paper, so 1.3, so like just the intro of the paper. The first section itself has 3 examples. And I hope that you may see the way to think about this is that when you choose an approximation, the natural gradient kind of picks out the relevant information. So when you do Newton's method, for example, natural gradients are expressed in terms of the gradient and the Hessian. And so if you go to like conjugate Bayesian model, you'll see the natural gradients are really kind of making these messages that you pass in message passing, like in Kalman filter. So this kind of gives you an idea of what kind of information you want to mine from the problem. And hopefully that helps you to design a structural variational approximation. So that's where we're kind of headed. And we have some new work by Wu Lin, which I think I'm not written in this one, which came out in ICML 2021, where there's more clues on how to choose structured approximation. This is still, not completely clear of how to do it, but there's some hints on there. I hope that gives you some ideas of what I'm saying.
Yeah, cool, thanks. I'll look into that.
And maybe just to follow on from that a little bit, Emti. So, everything here relies on being able to write down natural gradient, which means you need like conjugate exponential family Q distributions. How do you feel about that? There's obviously a lot of work in variational space on looking at Q distributions which go beyond that kind of construction. Is that something we should worry about? And I guess sort of slightly connected to that is, do you see the learning rule as something as more generally applicable outside of neural nets and GPs to other domains? And I guess that's maybe where these other types of Q distribution maybe have more chance.
Yeah, that's a great question. Yeah, it's surprising, right? Like so far, all the practical things that we want to do, I didn't have to go outside the mixture of exponential family. So which actually makes sense because tractable things that we are able to implement, they are, these are computations that we are able to kind of do in the conjugate exponential family. So like beta, like gamma distribution, the basis is very complicated. It's like log of some log of x, x and log of x, right? And this basis can then help you to fix a very complicated function, but the computation is easy because it's conjugate. So I think that there is a hope that maybe these kind of hierarchical variational models that people talk about, maybe some of those will come out and they would probably just build on the conjugate exponential family, right? Like not just use just Gaussian, but use maybe some kind of mixture of Gaussian is one thing that we tried, but some variants of those things where we pay more attention in putting structure in the variational approximation. If I have to say one thing about my work that every day comes up in all discussion that I have with my most collaborators is that I shouldn't be looking at the loss or the model, but rather we should be thinking about what to, mine from the model. The model is mining from the world through the data, but the posterior approximation is mining from the model. And so our structure of our variational approximation should somehow not mimic closely the structure of the model, but they should be trying to abstract it. So simplify and keep only the connections that are important. And this is where I think this Bayes duality goes, because it tries to ask this question of what Lagrange multipliers are big. So what connections in our graph are the most dominant ones? And you need to figure this out, So yeah, the hope is that somehow we get towards that. I don't know if that made sense, but I said it anyway.
Yeah, make it.
Right, is there any more questions from the room or on Zoom? Everyone seems content. Okay, thank you so much, Emti, for the talk and for giving it in spite of feeling ill. I really hope you feel better soon. Yeah, thank you so much from us for coming. Well, for giving it.
Thank you for inviting me. I'm always very happy to talk to more Bayesians. So thanks a lot.